Welcome back. Today I'd like to talk to you about directional derivatives and gradient vectors. And so let's start with a definition, and then we'll talk a little bit about what it means. So the derivative of a function f at some point, let's call it p sub 0 at x0, y0 in the direction of the unit vector u, which is u1 I plus u2 j is the number and so this is the derivative of f with respect to some direction, some path s, and this is in the direction of u at the point p0. Okay, this is going to be equal to the limit as s goes to 0 of f of x0 plus s times u1 y0 plus s times u2 minus f of x0 y0 divided by s, where s is some path. Okay, but the path, we're pointed in the direction u, and we're dealing with this derivative at point p0. Okay, so what we did recently is we talked about partial derivatives. And I told you that a partial derivative is basically a derivative in a direction of either x or of y. So if you have some surface, like let's say I have a little hill here, and I take a point on the hill, then I can ask about, well, what's the slope in, let's say, the x direction, and then maybe what's the slope in, say, the y direction, and those could be different. And we talked about that, and we talked about how we find those derivatives in the two different directions using partial derivatives. But what if I wanted to take the slope in some other direction? Let's say this is the direction u. Okay, so in other words, if I blew this up a little bit, here's the slope of my hill. I've got some point, let's call it p0. I've got some direction. This is called u. And I want to know what's the derivative in that direction. Okay, well, I don't know. How would I figure that out? That's what this section is about, is how do you find the derivative in a certain direction. Right now I know how to find the derivative in the x direction. I know how to find the derivative in the y direction. How do I find the derivative in just any old direction, u, where u is a unit vector? Remember, unit vectors represent direction. The scalar attached to a unit vector, if you multiply a unit vector by a scalar, that tells you the magnitude of that vector. So when I talk about a direction, I'm talking about a unit vector in particular. We call that u. Okay. There's a notation that I should introduce to you, and that notation is the following. So I can talk about df ds along a vector u at a point p. In other words, what's the directional derivative in the direction u at a point p? There's another way that I might write this, and that is d sub u of f evaluated at a point p0. So these are just the same thing. It's just two different ways to write what's the directional derivative in the direction u at a point p0. So both of these notations mean the same thing. All right, so what I want to start with is I wrote out this limit definition of what a directional derivative is. And it's kind of like take the derivative a little bit in the x direction and a little bit in the y direction based on the components of x and y in your unit vector u. And this should make some sense. And so let's just use the formula that I gave for this directional derivative to take a derivative. So let's do a quick example. Let's find the derivative of the function f of xy is equal to x squared plus xy at the point p0, which is 1, 2, in the direction of the unit vector u, which is 1 over the square root of 2 I plus 1 over the square root of 2 j. Okay, so I have a function that I want to take the derivative of in a specific direction, u. I could put a little arrow over the u if I wanted to. That's a vector. At the point, specifically, 1, 2. Okay, so I have my function, I have my unit vector, my direction, and I have my point. Those are the three things I really need to take one of these directional derivatives. Okay, so let's go about this now that we know everything that we need. So let's find the derivative with respect to s. No, sorry. Let's go back here. I want in the direction u at the point p0. Okay. The way that we can write this out is this is the limit as s goes to 0 of f of. Okay, so what goes in here? X sub 0. Well, x sub 0 is the specific point that I'm working with, and the specific point that I'm working with is 1, 2. So x0 is 1 plus 1 over root 2, which is my u sub 1, times s, comma, 2 plus 1 over the square root of 2 s. Then I subtract f of my point, specifically 1, 2, divided by s. So really, I just went in and plugged in what I knew. I know my x0, I know my y0, I know my u sub 1, I know my u sub 2. So I just plugged it all into this directional derivative formula. Okay, so now I have a limit. So let's start plugging things in. So this is just the limit as s goes to 0. And now I need to say, what is f of 1 plus 1 over root 2s, comma 2 plus 1 over root 2s? Well, if I plug these things in, I get the following. Well, I get x squared. So I get x component of that function, which is 1 plus 1 over square root of 2s, quantity squared, plus x times y. So x is 1 plus 1 over root 2s times y, which is 2 plus 1 over root 2s. And then I need to subtract f of the point 1, 2. So I need to subtract f of 1, 2. If I plug in 1, 2 to the original equation, what do I get out? I'd get 1 plus 2, so minus 3. So that f of the 0.12 is 3. Okay, divided by s. Okay, so I just took things, plugged them in, and now it's time to do a little bit of algebra. So let's square this. So I get the limit, s goes to 0. If I square this out, the first one squared, 1 squared is 1. Then I get 2 times the first times the second, which would give me the square root of 2 times s. Then I get the second one squared, which is 1/2 s squared. Okay. Then let's FOIL out this second piece. And I get 1 times 2, which is 2. I get 1 times square root 1 over square root 2s, and I get 2 times 1 over square root 2s, which is plus 3 times 1 over root 2s. Okay. And then I take 1 over root 2s times 1 over root 2s, which is 1 over 2s squared minus 3 all over s. Now we can combine some things. Okay. Something I noticed right off the bat is I get 1 plus 2 minus 3. So 3 minus 3. So all of these are gone. And now what do we have? We have some s's and we have some s squareds. How many s's do I have? So I'm still taking the limit as s goes to 0. S's, I have a square root of 2, and I have 3 over root 2s. So I have square root 2 plus 3 over root 2, all of that times s. And then I have some s squareds. I have a half of an s squared and a half of an s squared, which is 1s squared. So plus s squared all over s. And you notice everything on top has an s in it. So we could cancel an s everywhere, and I'd get the limit as s goes to 0 of one of these s's cancels one of these s's and one of these s's. So what's left over? I get root 2 plus 3 over root 2 plus s over 1. And now I can go ahead and plug in that s is equal to 0. If s is equal to 0, what comes out? Just square root of 2 plus 3 square roots of 2. Well, what's square root of 2 plus 3 square roots of 2? I guess I could kind of rationalize. Square root of 2 is 2 over the square root of 2. And then I got 3 over the square root of 2. So this is equal to this guy, square root of 2. That's the same thing as 2 over the square root of 2. I think you'll agree that these are the same. And so I could say that this is 5 over the square root of 2. And for some of you that will be enough, but some of you might be saying, hey, you didn't rationalize that denominator. So if you like, I could do that. I could multiply the top and bottom by the square root of 2, and I get that that's 5 square roots of 2 over 2. So this would be an appropriate answer. Also, this would be an appropriate answer. So what did I just figure out? Well, I just figured out what is the slope of this curve at a specific point in a certain direction, the direction of that unit vector that I started out with, which was 1 over square root of 2i, 1 over plus 1 over square root of 2j. So in that specific direction at the point 1, 2, what is the slope? Well, it's 5 over square root of 2. So that's pretty cool. Now, we know from previous classes that we don't usually end up taking the derivative by a limit. That's the hard way. That's kind of the definitional way of taking a derivative. So maybe you're asking yourself right now, is there an easier way to do this? And the answer is yes, in fact, there is. Okay, so let's look at an easier way. So we want to take the derivative of f with respect to s of u p sub 0, where u is a unit vector and p sub 0 is a known point. And so what we could do is we could use the chain rule on this guy, and I could say the following, that this is the partial derivative of f with respect to x, specifically at the point p0, times the derivative of x with respect to s, plus the partial of f with respect to y evaluated at p sub 0 times dy ds. Okay, so that is the chain rule. Now, what we would notice is, well, what are we talking about here when we say the change in x with respect to s? So if I look at this term, what is the change in x with respect to s? Well, that is the movement in the x direction over this parameter s. But we have that. We have the direction in the x direction. We have the change in direction in the x direction. We're calling that the x component of our unit vector. That's our direction, or our change in direction in x. So that's just u sub 1. So I could write this as partial of f with respect to x evaluated at p0 times u1 plus, similarly, partial of f with respect to y evaluated at p0 times u sub 2. Okay? Now, I want to even simplify this just a little bit more. What I could say is, well, notice that this kind of has the form of the result of a dot product. Let me write it out and see if you agree. So what if I took the dot product of two vectors, the first vector being the partial of f with respect to x evaluated at p0 in the I direction, plus the partial of f with respect to y evaluated at p0 in the j direction, and then I want to take that vector and dot it with my unit vector u1i plus u2j. Well, what would I do? Well, I would multiply the components of I together, so this guy and this guy would be multiplied, and then I would add the j component multiplied together. And so what would I get? I'd get what's sitting right here. And that's exactly what I want. So, and of course this, what's circled, is my derivative. So this gets me exactly what I want. So this I'm familiar with, this piece right here. This is called my unit vector u. So I'm dotting that together with another vector, and we don't have a notation for this other vector yet, but we're about to. And we're about to call it the gradient vector. And so I'm going to write it this way. It's kind of like an upside down triangle f, and it's a vector. So we're going to call this vector that we start with here, which is a partial with respect to x, I, plus partial with respect to y, j. That's called the gradient of f. So let me write that down. So a definition. The gradient vector of f of xy at a point p sub 0, which is x0, y0, is the vector gradient. That's not my best triangle I've ever drawn. Gradient of f is equal to the partial of f with respect to x, I, plus the partial of f with respect to y, j. And that's specifically at the point p sub 0. So if I wanted to make it very clear that that's at p sub 0, I could write it this way: evaluated at p sub 0, evaluated at p sub 0. So this is what I call the gradient vector. So now that I've named this the gradient vector, then I could write the following: that the directional derivative of f with direction u at point p0 is equal to the gradient of f evaluated at p sub 0 dotted with the unit vector u. Okay, so in other words, the derivative of f in a certain direction is the gradient of f dotted together with the direction in which you want to take the derivative. Okay, and we call this the directional derivative, and we call this little guy right here, this upside down triangle f, we call that the gradient of f. Okay, so let's do an example to see how this works out and how we can, this makes taking directional derivatives fairly easy. So, quick example. Let's find the directional derivative of f of xy is equal to 2xy minus 3y squared at the point 5, 5 with direction u is equal to 4i plus 3j. Now, a couple things to note. In order to find this directional derivative, I need three things. I need the function. I have the function. I need a point. I have the point. And I need a unit vector. Do I have a unit vector? No, in fact, that's not a unit vector. That vector is not going to have length 1. So this is not right. I actually need to turn that vector. That has a direction and a magnitude. I need it to have just magnitude 1 so that it's considered a unit vector. So I need to figure out, well, what is the length of that vector u? Well, the length would be the square root of 4 squared, which is 16, plus 3 squared, which is 9, which is the square root of 25, which is 5. So in other words, if I really want a unit vector here, or if I want u divided by the magnitude of u to make it a unit vector, that's going to be 4 divided by 5i plus 3 divided by 5j. Now we're talking about a unit vector, and this is the third piece that I need in order to compute this directional derivative. So now all I really need to do is I need to dot together my gradient vector with this unit vector. So I suppose I need to find what is the gradient vector? Well, gradient of f, I won't plug in the point yet. I'm just going to take two partial derivatives. So the partial derivative of the original function with respect to x is going to be 2y. And that's it, right? Because the other component, the 3y squared, its derivative is 0 with respect to x. So that's in the I direction. Plus, let's take a derivative with respect to y. That would be 2x. And then with respect to y, I'd get minus 6y. And that's in the j direction. So if I want to evaluate that specifically, let's say I want the gradient of f evaluated at this point, 5, 5, then that would give me 10i plus, if I evaluated this at 5, 5, I'd get 10 minus 30, which is negative 20, in the j direction. Okay, so the things I need to dot together are this gradient, which is 10i minus 20j, and this unit vector, which is 4/5 I plus 3/5 j. Dot those together, and I will get my directional derivative. So let's do it. So I need the gradient of f evaluated at 5, 5, dotted with this unit vector, which in this case is u divided by magnitude u. Both of those I know. The first one, that gradient, was 10i minus 20j. And I needed to dot that with my unit vector, which was 4/5 I plus 3/5 j. If I dot those two vectors together, I get 10 times 4/5 plus negative 20 times 3/5, which is equal to, well, 4/5 times 10 would be 8. And 3/5 times negative 20 would be what? Negative 4 times 3 is negative 12, which would give me an answer of negative 4. Okay, and so now it's good to go back and ask the question, so what is negative 4? What did I just figure out here? Negative 4 is the rate of change of this function in the direction u at the point 5, 5. So it's the derivative in a certain direction at a certain point. And so we can calculate not only the change in the x direction and the y direction of this function, we can calculate a change in any direction. We just have to know the gradient at that point, and we need to know the direction in which we want to take the derivative. And if you know those two things, you can find that directional derivative, which is pretty cool. Okay. So the next thing that I want to talk to you about is let's think again about these directional derivatives. Let's say you have a directional derivative of u in the direction of u of this function f. Now we know that the way that I find a directional derivative is I find the gradient of f and I dot it with a unit vector u. Now when I dot two vectors, what is it that I get? Well, ultimately I get a scalar, right? I get a number. It's not a vector anymore when you dot two vectors together. We know this from previous work. But what is it when I dot two vectors together? There's another way of thinking about it, and I did this back a ways when we were talking about vectors. And what I get out of this is the following. It's actually the magnitude of the projected vector in the direction of u. I'll draw a picture in a second, but let me write it. This is going to be the magnitude of the gradient vector times the cosine of theta, where theta is the angle between the two vectors. Okay, so let me draw this. So we have a gradient vector. Let's call this one the gradient of f. That's one vector. And I have a unit vector. Let's call that u. And I dot those two together. I also have an angle between the two vectors. Let's call it theta. What I know is this number that comes out is the magnitude of the projection of the gradient onto u. So I project down at a right angle, and I'll get a vector that is the projection of the gradient onto u. What's the length of that vector? Well, earlier we figured out that the magnitude or the length of this new projection vector is exactly what I have up here. It would be the magnitude of the gradient times cosine of theta, and that makes sense because what is the length of this new vector? Well, it's the magnitude of this vector times the cosine of this angle just by trigonometry. So I get that this directional derivative of f is the magnitude of the gradient times cosine of theta. Okay, so yes, that is true. Why do I care? Well, what's the biggest then that this directional derivative could ever be? What's the biggest number that could come out of this? Well, it depends on theta, right? Theta is going to control how big or small that number is. But what's the biggest that cosine of theta can ever be? Cosine of theta lives between -1 and 1. It always lives between -1 and 1. So if I wanted to make the directional derivative the biggest it could ever be, then cosine of theta would be 1. Anything other than 1 would make it smaller. Okay, because this is an absolute value, so this is a positive number up here. And the way you make a positive number as big as possible is you don't multiply it by a fraction. You'd multiply it by 1. So 1 is the biggest that cosine of theta could ever be, which means it would make the directional derivative the biggest it could ever be. Well, when is cosine of theta equal to 1? Well, that's when theta is equal to 0. Well, what do I mean? If theta is equal to 0, then what is the difference between the gradient and u? Here's the gradient, here's u. If theta was 0, then they're both pointing in the same direction. Then here's u, and the gradient of f, they're just pointing in the same direction. So in other words, where is the directional derivative the biggest it could ever be? In the direction of the gradient. Okay, so the gradient is the place where the slope is the greatest. In the same way, we could ask, well, where's the slope the smallest? Well, it's going to be where cosine of theta is -1. Where's cosine of theta -1? If I said cosine of theta equals -1, well, then theta would be equal to pi. And in other words, that means that the place, if this is my direction u, the place where I get the smallest derivative is when I'm pointing exactly away from the unit vector. So if I'm pointing in the same direction of the unit vector, I get the highest slope. And when I'm pointing in the opposite of that unit vector, I get the lowest slope. Very interesting. So if you ever want to know where is the highest slope possible at a point, it's in the direction of the gradient. And if you want to know where's the smallest slope you can get at a point, it's in the direction of the negative of the gradient. Okay. What also, another thing that's interesting is, what if cosine of theta was equal to 0? Where does that happen? Well, cosine of theta equals 0 when theta is pi over 2, right? So in other words, if the two vectors u, so here's my unit vector u, and let's say that my gradient vector, gradient of f, are at right angles to each other, or are orthogonal to each other, then what would we say about the slope in the direction u? Well, it would be 0, because we know that the directional derivative is the magnitude of the gradient times cosine of theta. Cosine of theta is 0, so we have no directional derivative in that direction. Okay, so that would give me that my directional derivative in the direction u of f would be the magnitude of the gradient times cosine of theta. But if cosine of theta is 0, then this would just be 0. And I get that my derivative is 0 in that orthogonal direction to the unit vector. Okay, so all of this is very interesting information, that if you're orthogonal to the unit vector, you have slope 0. If you are parallel to the unit vector, that's your greatest rate of change. And if you're parallel to the unit vector but pointing in the opposite direction, that's your smallest rate of change. All right. Just a quick example, like if you were writing a computer program or something, and in that computer program you wanted to make a river or something running down some mountains, and you wanted to know, well, which way does the water actually flow down these mountains? Well, it would actually point in the direction of the most slope. So if you wanted to know which way does water run, it runs in the direction of the gradient. So if you were programming some sort of like water feature into a computer graphics of some sort, you might want to tell the water, hey, water, flow in the direction of, actually not the gradient, because if you were wanting the water to flow upward, I guess you would go in the negative gradient, but if you wanted to flow downward, it would be towards the negative gradient. If you wanted the water to flow backward, so to speak, it would be in the direction of the gradient. Okay, so let's do a quick example. So find the direction. Where the curve g of xy is equal to y minus x squared has the greatest rate of change at the point -1, 0. Okay. So I know that the place where a curve is going to have its greatest rate of change is in the direction of the gradient vector. Now, a key word here is direction. Direction is always defined by a unit vector. So what I want is a unit vector that points in the same direction as my gradient. So what's the gradient, first of all? So if I wanted to find the gradient of g, then I take the partial of this function with respect to x, which is minus 2x in the I direction, and I want to take the partial with respect to y, which is 1j in the j direction. So this is my partial. Now I want to evaluate that gradient at the point -1, 0. Okay? And if I plug in -1, 0, I would get 2i plus j. Okay? Now the question is, so that is the right way, but is it a direction vector? In other words, is that a unit vector? And the answer is it is not. So I just need to take this vector and I need to divide it by its magnitude. So what is the magnitude of this vector, gradient g evaluated at -1, 0? It would be the square root of 2 squared, which is 4, plus 1 squared, which is 1. So it's the square root of 5. So if I want this direction, then I would just take that gradient of g evaluated at -1, 0, and I'd divide it by the magnitude of the gradient of g evaluated at -1, 0, which would be 2 over the square root of 5 in the I direction plus 1 over the square root of 5 in the j direction. And that would give me the direction in which that curve has the greatest rate of change at the point -1, 0. And then if you wanted to ask the question, well, what is that greatest rate of change? Well, now we're talking about something different. Now we're talking about a directional derivative, and that's what I did in the last example. Okay. One more thing that I want to talk about, and then I can let you go do some homework, and that is the fact that gradients and tangents are normal. Or in other words, they're orthogonal to each other. Okay? So let's say that I have a function f, and it is a parametric curve. So let's say we have f in two variables, x and y, but x is a function of t, and y is a function of t. And let's say that that equals something like c. That could be a level curve. Okay, so that's a level curve. So I could take the derivative of this function with respect to t. So let's take the derivative with respect to t of this function f of g of t, h of t. And the derivative of that curve, the derivative of c, is 0. Now, we can use the chain rule to break this up. And the chain rule would tell me that I would find the partial of f with respect to x times the derivative of x with respect to t plus the derivative of f with respect to y, and that's a partial, times dy dt, and that's equal to 0. If I think of this as a dot product, then what I get is this is just the gradient of f dotted with what? Well, dx dt in the I direction, dy dt in the j direction. So I could write it as dotted with dx dt in the I direction plus dy dt in the j direction. But what is this dx dt I plus dy dt j? Sometimes we could call that vector dr dt. Is this vector here. And dr dt is what we call the tangent vector. But what do I have here? I have a tangent vector times a gradient vector gives me 0. But that means that the tangent vector and the gradient vector are orthogonal to each other because they dot together to give me 0. Okay, so if you wanted to look at a picture of this, let's say that I have some level curve. I have an xy axis, and let's say I have a level curve. Then if I want to find, let's say I have a point here, then the tangent line to that curve, that's the tangent, and the gradient this would be the gradient of f. So my tangent vector and my gradient vector are going to be at a right angle to each other. Or in other words, they are going to be orthogonal to each other. Okay. So we can use a nice little formula to find an equation to a tangent. So here's a nice little formula that might be nice to know. That tangent to a level curve, if you know that the partial with respect to x at the point x0, y0 times x minus x0 plus the partial with respect to y of x0, y0 times y minus y0 is equal to 0. This in some sense is like the point slope equation of a line. And if you really wanted to solve this thing for y minus y0, then you would get something that was very, very nice. You would get kind of like that y minus y0 should be dy dx times x minus x0, which is exactly our point slope equation for a line. But this is just kind of broken up a little bit more into partials. Okay, so we can use this nice equation to find the tangent line to a level curve. All right. A couple other things that you really should know is we can use some algebra for gradients. The first thing is, let's say that I have a gradient of k, a constant, times a function f. Then that's just k times the gradient of f. So constants can move in and outside of gradients, mainly because a gradient is just a vector, right? This is a vector. This is a vector. And you can multiply a vector by a constant, and you just multiply each component by the constant. Also, if you have the gradient of a function f plus a function g, then that's the gradient of f plus the gradient of g. We have the gradient of f times g is going to be equal to, now this one's interesting, and it's almost kind of like a product rule of sorts, is it's going to be f times the gradient of g plus g times the gradient of f. And similarly, if we take the gradient of a quotient like f over g, then we also get kind of like a quotient rule. And we get that it's going to be g times the gradient of f minus f times the gradient, the gradient of g divided by g squared. Which this one should remind you exactly of the product rule. And this one should remind you exactly of the quotient rule. Because really, what is a gradient? It is a derivative. So when I say the gradient of some function that is a product, you should be thinking, okay, I'm taking the derivative of a product, so I need a product rule. And that's exactly true. Okay, the last thing that I want to say has to do with having 3 variables in a gradient, and really nothing changes. It does about exactly what you would think. If you have 3 variables, x, y, and z, then we would talk about the gradient of f being equal to the partial of f with respect to x in the I direction, plus the partial of f with respect to y in the j direction, plus the partial of f with respect to z in the k direction. And still, even in 3 variables, if you have a unit vector pointing in a certain direction and you want to take the directional derivative with respect to that unit vector, then you're still just going to take the gradient of f. But of course, the gradient of f now is in 3 variables, dot product with that unit vector, which now that unit vector is in 3 directions. Okay, so everything remains the same. You just add in that 3rd direction. Okay, that gives you everything you need. Good luck on homework.